All right, the next video is 23 minutes long. Ines Hipolito, Dysfunctional Markov Blankets, From Stuck States to Adaptation.
Hi everyone, I'll be presenting today Dysfunctional Markov Blankets, From Stuck States to Adaptation. This is a paper that has been in progress for quite some time, and it is a collaboration with Mao Albarracin, Alex Kiefer, and Daniel Friedman. So I want to start by highlighting that there are stuck systems or stuck states all around us, and that we find that example in neural cognitive levels, such as in OCD patterns, in PTSD trauma cycles, or in addiction circuits. Then on the social or ecological scale, we find it, for example, in poverty traps, in echo chambers and market monopolies and climate tipping points. Then in AI, we also find them, for example, in large language models loops, who isn't been stuck in a I apologize kind of cycle. Then in reinforcement learning local minima, in recommendation filter bubbles, and in neural networks training fails. So what these kinds of systems share is that they are some sort of critical threshold. They have or present self-reinforcing loops, and they have this persistence to change. So they tend to remain in the same state, hence why they are stuck. So then the core problem is going to be a sort of a paradox. So the view is that systems, adaptive or complex systems, coupled with the environment, they should adapt, but sometimes they don't. So then from this perspective, a few questions become salient. Why do flexible systems become so rigid and do not have that flexibility to adapt to the environment? How do these adaptive boundaries between the system and the environment break down? And what maintains that dysfunctional state? What is there that must be so strong that the system cannot change to a different or look for or act for to attain a different, more preferable kind of state? So then, of course, that these are presented as challenges because there is an ever-changing world and the system that needs to adapt to that ever-changing world. And it seems like existing approaches, such as dynamical systems theory and network science, still have some limitations to quantify and address this kind of phenomenon that we call a dysfunction. So then, from our perspective, we need a framework that unifies this explanation. So we need three things. First, we need to identify and characterize dysfunctional states. Then we need to provide a mechanistic explanation for the stuck states. And finally, we need to offer a principled approach to designing these kinds of interventions. And that's what we set up to do in this paper, and that I'll be presenting to you. So our framework bridges theoretical frameworks from complex systems theory and the free energy principle. The main or core concepts that are going to be useful are notions such as emergence, self-organization, and adaptation from complex systems theory, and coupling, self-maintenance, and free energy from the free energy principle. By utilizing these two frameworks, we developed a construct that we defined as dysfunctional Markov blankets. And with that, we hope that we will offer a formal theory of systems dysfunction. And we hope to develop quantifiable measures for this phenomenon of stuckness. And finally, practical recovery strategies so that we can act upon the system that is stuck in a therapeutic way, and we hope to kick the system out of that stuck state into a healthy state. Okay, so as to adaptive systems, we all know that they are comprised by components which interact, and from that interaction we observe some sort of emergence. For example, in the case of an immune response, we have different immune cells, each one with a specific role, and they interact in the form of cell signaling, recognition of events, and that interaction then gives rise to emergence that we observe in the form of coordinated defense or system-level memory. Then, from the free energy principle, which we are very acquainted with in this conference, we learn that systems that exist act to minimize their free energy. And further to that, the understanding or the insight is that systems are coupled with the environment and they act upon the environment to precisely attain or look for more preferable states for their self-maintenance. And we can explain that behavior through active inference. Then another very useful construct is Markov blankets. Of course, the framework is dysfunctional Markov blankets. And the Markov blanket, as we all know, is a statistical boundary between what is inside of the system and what is outside. But further to that, an important insight is the conditional independence between internal and external states, which give the system sort of a very important boundary to have a distinction between the self and the no self. And that can be seen also through the notion of it's an operationally closed system, a system that self-organizes and maintains itself. For that maintenance, it's also quite important that it is thermodynamically open. It is an open system. It's not a closed system. And that's what allows them to remain alive by adjusting to the environment. And here you see, for example, we have neurons in the form of internal states that could be part of a network. So a key innovation concept that we bring in is the notion of selectability. And selectability is a system's capacity to explore, navigate, and select among possible states. These can also be seen as the system having multi-stability, many points that are afforded to the system in the environment such that the system can be healthy in that navigation. So you can see that, for example, that comes represented here in the form of state A, B, C, or D. Different points that the system can explore within the environment and select the most preferable ones. And the notion of selectability allows us to think about state space accessibility or affordances, the adaptation capacity, and the boundary flexibility to adapt rather than being rigid and stuck in a particular state. So then within the free energy principle, we can think through that paradox. It becomes if systems minimize free energy, if they accord to the principle, why would they get stuck? Does the principle not work, or is it the system that is not in a stuck state? So then what we realize is that what is really within the paradox is that we cannot explain these persistent maladaptive states, and there is not really a formal treatment of the dysfunction. So then there is a missing link between theory and intervention, and our solution is the dysfunctional Markov blankets. There are two types of boundary dysfunction that we can observe in these systems that are not adjusted, attuned, adapt to the environment. So they can come in the form of stuck states or blanket breakdown. And stuck states, I mentioned this in the first slide. And for example, in the case of depression, what we observe is rigid kinds of thought patterns, reduced emotional flexibility, impaired social information processing, and shortcuts bypassing healthy emotional regulation. And in a more general way, we can define these stuck states as the self-reinforcing kind of cycles, being trapped in deep energy wells and being resistant to environmental perturbation. Then on the other hand, we have blanket breakdown. And an example of this is the immune system, when the immune system attacks its own tissue. And what happens here is a very interesting phenomenon of excessive permeability on the boundary of the blanket, right? Loss of system integrity. So the self-no self distinction. The system doesn't know what's self and what is not self. That's the loss of system integrity because of the boundary dissolution. Okay, so then we arrive at the definition of the dysfunctional Markov blankets. And this is a statistical boundary that contrastingly has lost its adaptive capacity for effective mediation between internal and external states. And the key characteristics of the dysfunctional Markov blankets are that the system is persistent in high free energy despite adaptation attempts. And what we observe is the breakdown in information processing and the loss of effective environmental coupling. I will unpack this further, but let me just situate us for a moment. So we will go from the framework to practical tools to cross-scale applications. That's where we would like to go. So to do that, we need to first define quantifiable measures, then identify a dysfunction index, and finally, the recovery metrics. Then as to practical tools, we need adaptive perturbations in order to kick the system out of the valley, and recovery strategies. And this is on a more therapeutic kind of side. And hopefully we'll be able to apply these across scales. So now looking at the framework itself, the first thing that we need to do is to find that dysfunction index. And what that is going to help us do is to measure and identify and delineate the dysfunction. It will measure the information flowing through the wrong channels, like a diagnostic kind of tool that spots the system bypass. And the higher the value, the more dysfunction. For example, like a cell with a compromised membrane. Then we will need also a recovery metric. And this will be a progress kind of indicator for us. So it shows a dysfunction reduction. And the thought here is that we ask ourselves, are we fixing the bypass problem? So then we will need in order to advance with that, we need the landscape reshaping, kind of like bringing out a new geography of points that are afforded to the system, making sure that we don't get stuck again. And hopefully we'll attain the system's adaptability, where we find the question, can it explore and respond flexibly to the environment? So why are these two measures relevant? Well, they will serve the role of being universal tools across scales. We will be able to apply them to all scales from cells to ecosystems, and they will help us diagnose and track recovery and guide our next stage, which is the intervention design. Okay, so now moving to practical tools, adaptive perturbations, and recovery strategies. We have adaptive perturbations here playing a crucial role, and an adaptive perturbation is going to be a controlled intervention that temporarily disrupts a system state to facilitate adaptive change. And what we mean by these, or Our goal is not simply to push a system out of being stuck, but it is to help it to become more resilient, precisely to make sure that it doesn't come back to the stuck state, as you can see an illustration here on the graph below. So we define the adaptive perturbation design as, in the first term, as traditional intervention approach, where we would like to nudge the system towards these better states such that it adapts based on the system's response. Then with the middle term, we can reshape the energy landscape, have a different sort of more flexible geography that makes it harder to get stuck. Again, like smoothing out the deep valleys. And then finally, we can promote exploration, and that means help the system discover new affordances, new possibilities, hence enhance adaptability. There are kind of like two examples of adaptive perturbations that I just want to mention, and one is by the parameter changes, where, for example, you can think of that as a temperature modification in cellular environments. And the other one is the external force or input. An example of that is transcranial magnetic stimulation. So why is this adaptive perturbation relevant? Well, it combines three intervention strategies. Self-adjusting, all parameters will adapt over time, and it includes a balance between immediate improvement, long-term prevention, and future adaptability. The practical impact of an adaptive perturbation is that it will help us guide for designing interventions and work across different scales and prevent the kind of, so to speak, band-aid solutions. Right, so then why do perturbations matter in the end? Well, for the stuck states, they're going to be very relevant to help us overcome energy barriers, break self-reinforcing cycles, and enable the system to have more states and the capacity to navigate and explore the environment and select the states that are going to be much more preferable to the continuation and maintenance and self-maintenance and self-organization of the system itself. In the case of the blanket breakdown, this is the case of, for example, the immune system that has lost the capacity to differentiate between what is self and what is no self and attacks its own tissue, then utilizing an adaptive perturbation will be useful to restore boundary function, to stabilize information flow, and to reset system dynamics, and therefore repair the capacity of the system ultimately to recognize what's self and what is no self, what is internal states, what is external states. Okay, so I will recap the journey now from the dysfunction to the recovery. So first, we need to measure the dysfunction. Then we need to track the recovery. Then we will need to design interventions, and we do that through the adaptive perturbation to implement the recovery. Finally, we need to monitor that kind of recovery such that we now have been able to get the system to be adapted to the environment rather than just in a very short term. So key relationships that come up within this journey include going from higher dysfunction to stronger perturbation that is required, going to better recovery to reduced intervention strength, and going from more selectability to greater adaptation capacity. Future directions where we need to go is to extend this mathematical formalism to non-ergodic systems, to multiple timescale dynamics, and coupled systems interactions. In order to do that, we also need to develop measurement tools such as real-time dysfunction metrics, early warning indicators, that can predict a tipping point or a point of no return, and then we can apply a preventive measure and cross-scale validity tests. Some of the implementation challenges that we can see include, of course, measurement, intervention, validation, and scaling up. And in order to address them, we will need better tools, more precise tools, standard tests, and infrastructure. The potential impact of this framework is, like I said, across scales. In healthcare, for example, we can look into therapeutics for any sort of disease kind of cycles. It includes mental health and aging patterns. In climate action, we can apply this framework to tipping points as a preventive measure and to restoration. In AI, we can apply to develop more robust AI. We can also apply it to make more smoother ethical and governance measures for safety in AI, as well as can help us design bio-inspired AI such that it's a system that is more adapted and hence more effective. Finally, in social systems, we can also apply this framework for policy design, for economical stability and social cohesion. And coming to the end, call for action. Research priorities include developing standardized metrics and build shared data sets, create open source tools, and establish cross-disciplinary teams. So please join us in theory development, tool creation, application testing, and knowledge sharing. Conclusion and takeaways. So we went in this journey from dysfunctional systems that we observe that are stuck in a local minimum, and we want to develop a perturbation in order to help the system become more resilient and adapt to the environment out of the stuck state, and hence a full recovery in the long term. So then key takeaways are that we hope that we have developed the foundations for a formal theory of system dysfunction, quantifiable measures for the stuckness phenomenon, and a practical recovery strategy that can be applied, that can be further in the future applied to different scales. Thank you so much for your time. Please do not hesitate to contact myself or any of the authors if you'd like to engage or learn more about this work.